So an ideal M in a ring R is called maximal if there's no ideal I that fits strictly between M and R. So this is proper containment. There's no ideal I that fits in between M and the entire ring R. So here's example. 2z is maximal in the integers. So the even integers is a maximal ideal in the set of integers, but compare that with 4z. So multiples of 4, that's an ideal in the integers. This is not maximal, however, because I can find an ideal that sits properly between 4z and z. The even integers do. Well, this is proper containment. Proper containment. Okay. So let's state the main theorem concerning maximal ideals. So the theorem is, let M be an ideal in a commutative ring R. So the ring has to be commutative. Then M is maximal if and only if, so if and only if the factor ring R mod M is a field. So this is a nice characterization of maximal ideals. Let's go the forward direction. First, assume M is maximal. So I want to prove that the factor ring is a field. Let's remember what a field is. A field has to be a commutative ring. But since R is commutative, multiplication in the factor ring also commutative. So I have a commutative ring. A field also has to be a division ring. That means every non-zero element has an inverse. So in order to prove that this is a field, that's what I need to do. So I'm going to take an element in the factor ring, A plus M, that's in my factor ring, and I want to take this to be non-zero. Now what non-zero means in the factor ring is that A cannot be in M. Because if A was in M, then this would be the zero element in the factor ring. So somehow I have to use the definition of a maximal ideal, meaning I need to play around with this condition here. To do so, I'm going to define a set I. It's going to be an ideal. So I will be the set A times R. So I'm taking this A, and I'm going to multiply by every possible element in the ring R, and then I'm going to add M. So this is definitely a set. It's a set of every element I can get where I do little a times something in R plus something in M. And I claim that I is an ideal. Well, let's check. To verify something's an ideal by the definition, I need to look at little r times I. That is, now the multiplication is commutative, so this is A little r big R plus little r M. So I'm distributing the R across and using the fact that the ring is commutative to put the R next to the big R. Now, the ring R is closed under multiplication, so this is back in R. So this little r times big R back in the ring. And M is an ideal. It's an ideal. So when I do little r times m, I land back in M. So this is definitely a subset of AR plus M. That's my set I. Therefore, I is an ideal. I have a commutative ring, so I don't need to check the little r multiplied on the right. This shows I is an ideal. Furthermore, so I is an ideal. And M is a proper subset of I. The 0 element is in the ring R, so I can get anything in M I want back by taking A times 0 plus something in M. So M is definitely a subset, but it's also a proper subset because A was not in M. A was not in M, so you could find an element in the ideal I that's not in M. Now, M is a maximal ideal. This condition is true. So that means I has to equal the entire ring. Because if it wasn't the entire ring, if it were a proper subset of the entire ring, then I'd find an ideal I that satisfied this condition that I said no ideal could satisfy. So I is the entire ring. And what that means is the identity, the multiplicative identity 1 is in I. Everything in the ring R is in I, in particular 1. And so there are elements R in the ring and M in the ideal such that 1 is equal to AR plus M. So my ideal I looks like this. Since 1 is in the ideal, I could write 1 in this form. Thus, watch this. A plus M times this little r plus M. Definition of multiplication in the factor ring is AR plus M. Now, AR is equal to 1 minus little m plus m. I just rearranged this condition. And that, since little m is in my set M, is 1 plus m. That is the multiplicative identity in the factor ring. So A times A plus M, this element, times another element gives me 1. That's an inverse. So thus, A plus M inverse exists. That's the end of this direction of the proof, because now I have a field. I took a non-zero element in my ring. I showed that it has a multiplicative inverse. The ring is commutative. That means I have a field. Okay, now for the other direction. Now I'm going to assume I have a field, and I want to prove that M has to be maximal. So I'm going to take an ideal I, such that M is a proper subset of I. I hope that I could prove that I has to be equal to the entire ring R. So I will show that the ideal I has to be the entire ring, because then this condition cannot be satisfied. So the way I'm going to do that is I'm going to take an element A in I, but not M. I could do that because M is properly contained in I. And then I'm going to take a B in the ring such that A plus M times B plus M is 1 plus M. I'm using the fact that I have a field. That means that every non-zero element, that's why I took A to be an I but not M. This is a non-zero element. Every non-zero element has a multiplicative inverse. Let's call it B plus M. Now, 1 is in here. So 1 happens to be in this coset. So that means there is a 1, there is an element M in my ideal such that AB plus M is equal to 1. How am I getting that? The 1 is in this set, and this, if you do the multiplication in the factor ring, is AB plus M. So I could write 1 as AB plus something in M. Now, A times B, that's in my ideal I. Why? A is in I. And part of the definition of an ideal is whenever you take something in the ideal and multiply by anything else, you always land back in the ideal. So this is in I. Little m, that's also in I. So that means the multiplicative identity has to be in I. So to finish things up, so the number 1 is in I. And once you have the number 1, once you have the multiplicative identity in an ideal, it has to be the entire ring. It's game over at that point, because then if I take any other element R, so any element R, I could do 1 times R. 1 is in the ideal. That means 1 times R is also in the ideal. This is in your ideal for all elements R in the ring. That means every element in the ring is in the ideal. So I is equal to R. And that's the end of the proof. So that shows that if you have a maximal ideal, your maximal ideal is an equivalent condition to the factor ring being a field. All right, great.